All right, so today we're going to start. So this is really chapter 2. And multi-degree of freedom, which we'll call MDOF. Before it was called SDOF, single degree of freedom. Now we have multiple degree of freedom. Let's say vibrations, and that's it. Okay, so on the previous section for the single degree of freedom, I redid 3 times the derivation. I did the derivation for the for what we call the free vibration, which is without the damper and the force. Then I did the derivation of the equation of motion for the damp free problem, and then we redo the derivation for the force vibration, no? Okay, that was, so you get, repetition is the learning. In this case, in this chapter, I'm not going to do 3 times the derivation. I'm just going to do it once, the one which is the most general, the force vibration with the damping, and then what I'm going to do is simplify the equations from that one, okay, for each different case, all right? So the first thing would be equation of motions. So read this equation of motion for force vibration. Okay, so we're going to do the figure that you cannot saw on the screen. So we need 2 masses. All right, so this mass may be connected by spring, damper. We have the same thing over here. And the same thing on that side. All right, so maybe I should have done that one longer. It doesn't matter. This will be K1, K2, K3, C1, C2, C3. Okay, let's assume no friction. All right, I forgot to put here. This will be M1, M2. And here we need to specify the force vibration. So this could be F1 of T. This could be F2 of T. And on the same one, we're going to define here as being X2. And this will be X1. Okay, but again, the procedure, everything remains the same as we did before, okay? So first step is always to do a free body diagram or figure. So let's do the figure over here. So we need to do the one for the 2 blocks. So again, I'm going to do so step 1. is always some type of figure or sketch. All right, so you're gonna have here, if you do the mass, I don't know how to do this one really. Okay, let me do two. Really, this is the way I would like to see it, but I think it would be more clear another way. But let's try to follow the same procedure as we had before. Okay, so this will be for M1. This will be for M2. Okay, so if we look at M1 here, pay attention. All right. So on this side, we're gonna have effects for the spring, no? So if we start from this end, if we move this mass, this is gonna move X1, no? All right. So this is gonna create a force over here. KX1. And here we're gonna have K1 X1, sorry, and this would be C1 C X dot 1, no? All right. Now, what we need to be careful is here. On this side. So on this side, what are we gonna have? This will be spring K2. But now this one will move how much? It will move whatever you pull it from this one minus whatever this one has moved. Yeah? Because it's relative motion now. So it becomes K2 X sub 2 minus X sub 1. We're going to have the same thing right here, would be C sub 2 of X dot 2 minus X dot sub 1. And let's not forget, we still have the force here, F1 of t, which is this one over here. Okay, and the motion of this one will be what? Will be M1 X double dot 1. All right, so it's the same as before, but we need to be careful here. Okay, and I'm not putting here by now the components on the y direction because the motion will only be on the x, okay? Otherwise, it's going to be too many things. So now we do the same thing for this figure. What are you going to have in block 2? You're going to have the reaction from these two forces, no? So in this 2, you should have basically the K2 in that direction and the C2 in that direction. So this should be K2 X2 minus X1. And C2 X dot sub 2 minus X dot sub 1. Oops, sorry, this is here. I'm going too fast, I want to sketch over here. Okay, and then on this one, we're going to have the reactions from the wall to this mass. So that will be here K3 X2, C3 X dot 2. Okay, oh, maybe, do you see why did I plot this one to the left? Because the initial assumption was that I was moving everything to the right, no? Okay, so if you want, you can reverse everything. You can do the first assumption that you move everything to the left, then these two will be reversed, no? Yeah? So before writing the equation of motion, this is important. Make an assumption about how everything is going to move. So you can do consistently the equation of motion. In this case, what we assume is that both everything will move into the right together, no? Yeah? All right. So now, step 2, what is step 2? Step 2 is to write down the equation of motion by just writing the equation, summation of forces equals to MA. So on an exam, since you're going to have the exam, I want to see the procedure, and to me, if there is no figure, there is no way for you to get the equations. That makes sense or no? Okay? All right. So obviously, we need to write down one equation for this fibroid diagram, one equation for this one, no? Okay, so let's say for M1, what will be the equation? We can just rewrite over here, will be minus K1 X1 minus C1 X dot 1 plus K2 X2 minus X1 plus C2 X dot 2 minus X dot 1 plus F1 of T equal to M1 X double dot 1. Okay, and for block M2, what will you have? So if we follow this one, will be to have minus values everywhere. So let's look at this field. We'll have minus K2 X2 minus X1 minus C2 X dot 2 minus X dot 1 minus K3 X2 minus C3 X dot 2 plus F2 of T equal to M sub 2 X double dot sub 2. All right, so now we're going to go to the next page. What we need to do is simplify these equations, okay, and see what happens. All right, so let's see what we get. All right, so on the first one, we can get M sub 1 X double dot 1. So I'm going to be moving everything to the right. Then plus C1 X dot 1. So I just move this this time here. I move this one to the right, this one to the right. No? Now can I do anything with these ones? No. So I'm just going to rewrite the equation basically. Yeah, I'm just going to write the equation. There's no specific order you need to follow. So let's just do it. Let's do it that way. Minus K2, doesn't matter. X2 minus X1. So that one moves to the other side. Minus C2, X dot 2 minus X dot 1. And this should be equal to F1 of T. I do the same thing with the other one. We're gonna have m sub 2 x double dot 2 plus C3 x dot 2 plus K2 x2 minus x1 plus C2 x dot 2 minus x dot 1 plus, oops, I think here I forgot a K, no, maybe? Yeah, I forgot on the first equation, you see I forgot the K1x, no? So let's put it here, would be plus K1x. In the ones I have it, so here would be this, K2 plus, I don't have to forget here, plus the K3x sub 2. This one I put it, so I think now I have everything equals F2 of t. Okay, but this is going to become a lot more clear once we rewrite it into the matrix form. Or in matrix form, so let's see if we can do it together. So the first term we're going to have here is x double dot 1, x double dot 2. All right, so if you look at this equation, the first equation here, M1, is only in function of x double dot 1, no? So this term should be going where? M1. Is it any term in function of x double dot 2 on the first equation? The answer is no. So this term here should be 0. The second equation only had a term M2 in function of x double dot 2. So we should that term go over here. And here is 0, no? Okay, I hope you understand how I'm going from this equation to this equation. Now, plus, we will do the same now with the dampings. So before I close this, let's see how much space I'm going to need. All right, so I think that should be enough, hopefully. So what I'm looking here is to put over here now x dot 1, x dot 2. So hopefully that should be enough. All right, so what is the term in function of x1 that we have? X dot 1. So here we're going to have C1, and then maybe you see here we're going to have C2, no? Yeah, so that means here we're going to have C1 plus C2, C1 plus C2, and we are just left over with this one in function of x dot 2, and this one is negative, so minus C sub 2. So the top line of the matrix is for the first equation, all right? Now for the second equation, what do we have here for x dot 1? So you see this one is in function of x dot 2, x dot 2, there's only one x dot 1, and that will be minus C2. Okay, it's this term over here. And now we have for x dot 2, we're going to have C3 x dot 2 plus C2 x dot 2. So that will be C2 plus C3. All right, and we do exactly the same thing for the case, for the stiffnesses. So let's see. The first one will give you what? In function of x1, you have k1 plus k2, no? From the second term, so k1 plus k2. And this term is a function of x2, so it should be minus k2. If we go to the second equation, that will define the second line of the matrix notation. We'll have, so generally you have here the same thing, minus k2, so it will be the x1 term. It's this one minus k2. It's going from here. All right, and now for x2, you're going to have k2x2 and k3x2. So that should be now k2 plus k3. All right, so now we did derive the most general equation of motion, and the step 3, the general step 3 would be what? To find the solution to the differential equation, no? In order to find the solution, what do you need to do? Assume the solution, correct? You substitute into the equation, and then you need to solve the characteristic equation for the natural frequency, what will be an eigenvalue. All right, so in this case here, we're going to do the same steps as before. We're first going to do it for the free vibration of the undamped system, and then we do it for the free vibration of the damped system, and then we do it for this equation. All right, so now first solution is going to be free vibration so what does the term free vibration means? F1, F2 equal to 0 of undamped. So what does undamped mean? C1 will be equal to C2 will be equal to 0. And here you can write system. Okay, so you can write here the equation of motion reduces to what? So basically this is 0 and all this matrix is 0. So we're going to have M1, 0, 0, and 2. X double dot 1, X double dot 2, plus K1 plus K2 minus K2 minus K2, K2 plus K3. X1, X2 is equal to 0, 0. Okay, so in order to solve this system, we're going to follow again the same procedure. First thing is to assume solution. But once again, this time I'm not going to give as many details as before, okay? So the assumed solution should be of what form? X of t will be equal to capital X E I. Before I remember either lowercase omega for the first frequency, but here it might be two different frequency of excitation for F1 and F2, no? All right, so, and in this case, it's not F1 and F2 anyway, so we just call this one, E omega t, okay? Lambda, this is lambda, sorry. All right, so this equation actually means what? Okay, so this equation actually implies what? That we are really having two solutions, x1 equal to capital X1 EI lambda 1t, or x2 equal to capital X2 EI of lambda 2t, no? Okay, so I'm not going to do it again, but what should we do now? We should take the first derivative of this. We should give you what? X of 1, E lambda 1, E of I omega t. Same thing for this one, and take the second derivative, no? And then we go and substitute into the equation of motion. So I'm just going to say over here, substituting into equation of motion. What are we going to get? We can factor by the EI lambda t. And here you will have, so I mean, if we need to do that in detail, we can do it, but. So this one takes twice the derivative, so it should be in function of the lambda square, no? Correct? And it should be minus because I squared equal to -1. Yeah? Okay, so then we're going to have here minus M1 lambda 1 squared, sorry, minus lambda squared, no lambda 1. Forget about the lambda 1 here. Okay? And then basically the factor term, this one will be unchanged because in function of x. So that will be plus K1 plus K2. So I'm first going to this one, no? This one will be minus M1 lambda squared, no? Okay? This one will just be K1 plus K2. Correct? So that's really everything we have for the first equation. Right? Now we do the same thing for this one. What are you gonna have? You're gonna have the same thing for this one, but this will be in function of x2. Yeah, so it would be what? Would be minus, will be on this side, m2 lambda square plus k2 plus k3. Let me add here, this might be a little bit more clear for you what I'm doing. This is over here, capital X1, capital X2. Okay. All right, so okay, sorry, forgot. So now here, this term over here should be minus K2. You see, I forgot. This term over here for X1 should be minus K2. So before, for the sigma degree of freedom, we only had one equation, but basically the same procedure. Here, what we need to satisfy is this equation. So when will this equation be satisfied? Either when x1, so this term here, epsilon e lambda 1t x1 x2 is equal to 0, which this is going to happen when x1 and x2 are equal to 0, correct? Could be the first solution, but that's not the one of interest. Or it will be equal to 0 when this term over here is 0. Okay? So when would be this term equal to 0? From mathematics, you can solve when this system is 0 if you find the determinant of that system. Okay? So the first solution is when x1, x2 is equal to 0, which we will call the trivial solution. That one is of no interest. All right? The one we want to find is when this term here will be equal to 0, and then we need to solve for the roots of lambda. That will be lambda 1, lambda 2. So let me write over here, 96. So the previous equation is satisfied if and only if, that's what my double if means over there. Try to zoom a little bit. All right. Only if x1 equal x2 equal to 0, all right, which will yield to the trivial solution, meaning that we will have here, all this side will be equal to 0, this will be equal to 0, correct? Or when this term over here into bracket is equal to 0, which means that the determinant of this term over here in brackets, let me write down, minus m1 lambda square plus k1 plus k2 minus k2 minus m2 lambda square plus k2 plus k3 minus k2 So 1, 2. Okay, so this is when the solution is when this will be equal to 0. In order to know when this is equal to 0, you need to solve for the determinant, okay, of this matrix. If we find the determinant of this one, what do you need to do? This one times this term minus this term times this term. No? Okay, so here I'm going to give you the solution right away. This actually should give you the equation m1 m2 lambda to the fourth minus k1 plus k2 m2 plus k2 plus k3 m sub 1, or this one in function of lambda square plus k1 plus k2 times k2 plus k3 minus k2 square equal to 0. Okay, so this equation here is known, above equation is known as the characteristic equation. So you see that equation is in function of lambda to the fourth lambda squared, no? So I could say the above equation is known as the characteristic equation, and it is a quadratic equation for lambda squared. I don't know if I'm being very clear. What I'm meaning is that if we take lambda square as being the variable, this becomes what? Lambda square, and this one would just be lambda, no? So this becomes a normal quadratic equation. This would actually be called a B quadratic equation, but we cannot put everything, all right? So the solution above equation is known as the characteristic equation, and it's a quadratic equation, and it is a quadratic equation for lambda square, for which the solution is. So basically, what would you have to do? Lambda should be equal minus b plus minus b squared minus 4ac. This is the general form. Yeah, divided by 2a. I mean, this is the general form. You know what is a, you know what is b. So this will actually give you lambda 1, 2 will be equal to what? 1/2 of K1 plus K2 2 plus K2 plus K3 M1. So that would be the minus B, no? Is this term over here? Minus B. Then we're gonna have the plus minus be this term, 1/2 of, let's see. Yeah, sorry. So second term will be reduces to K1 plus K2 M2 plus K2 plus K3 M1 divided by M1 M2 square. I think I forgot here a term. Forgot here to put under this one M1 M2, no? Looks like. So let me put right here, divided. I'm going to do it in a different form. M1 M2. Okay, and now would be minus 4AC minus 4. Let me just write it as I have it on the class note, minus 4, and then this term will be here. K1 plus K2 K2 plus K3 minus K2 square divided by M1, M2, and everything should be the square root. Okay. I will have to check this one again because this is minus b, that one makes sense. But now minus 4ac. You should cancel that one, but then we have the 2am again, no? All right, guys, and here we're solving symbolically, but remember that in the primes, you're gonna have values over here. So in most cases, what you're gonna do is what? Most cases, what you're gonna do is use MATLAB in order to solve this. Okay? What happens is that you need to know, and we do that an example, what MATLAB is gonna give you, okay? All right, so it should give you now the two frequencies, lambda 1, lambda 2. That is the one actually that I wrote over here, no? Lambda 1, lambda 2 will be those two frequencies. But here, in order to simplify notation, I just put lambda. Okay? All right? That's why I did not put lambda 1, lambda 2. But yeah, the solution should be lambda 1, lambda 2. Okay. So now what's important to know is that now here, I did here, I forgot to put something. What is my mistake that I've done over here? Let's see if somebody can picture. This is the solution of what? Of lambda square, no? Lambda square, lambda 2, because that is what becomes my variable. Okay, so lambda over here so if you want here, lambda square is known as the eigenvalue, which is a German name for meaning proper value, okay? The translation will be proper value, eigenvalue, all right? Lambda square is known as the eigenvalue that physically represents the natural frequency. So basically, lambda square is equal to the natural frequency. So, sorry for that. In our case, what? Lambda 1 square equal to omega 1 square. This is the natural frequency of the mass M1. And similarly, you can say lambda 2 square equal to omega 2 square is the natural frequency of M2. Okay, so what does that mean? That if we go to this figure, lambda 1 square gives you the natural frequency of this block, lambda 2 square gives you the natural frequency of this block. Okay? All right, so now comes what is important. is that what do we say? We say that this could move either together, or they can move opposite, or they can move along each other, no? Okay, so let's see how mathematically we can show that. So what's going to happen is that, mathematically speaking, all right, so where was that equation here? All right, so each eigenvalue, lambda 1 square, lambda 2 square, is attached to an eigenvector, but personally, I'm going to call it here, I think it's more appropriate for vibration, mode shape. That is determined as follows. All right, so here pay attention. This is not difficult, but sometimes it's easier with values than with variables. So the first thing we're going to do, so case 1, we're going to say that lambda square equal to lambda 1 square. Okay, what we need to do now is that we need to go back to this equation. All right? Actually, we need to add one thing to this equation, but we need to go back to this equation here. So now what we're going to do is we're going to go back to this equation. We're going to replace the lambda by lambda 1 first. So here we're going to have x1, x2, no? So for lambda 1 square here, we're going to find what would be then the solution x1 and x2. Yeah? Then we do the same thing. We substitute here by lambda 2. And then we find what is the solution for x1, x2. Okay? So that's what we need to do. Let's see if we have time to finish that. And then next time we do an example. All right, so in that case, we're going to have the equation EI lambda 1t should be, I'm going to start going a bit faster to write down. So you will have minus m1 lambda 1 square plus k1 plus k2. You're going to have at the bottom minus m2 lambda 1 square plus k2 plus k3. You have minus k2 minus k2. Here we're going to have x capital 1, x capital 2. And this should be equal to 0. Okay, so we need to have this satisfied. All right, so here's called, since this system needs to be valid for, this is now moving, okay? So this is valid for any time t. Okay, so in order to have this equal to 0, what do we need to have? If we look at the top equation, what's going to happen? You need to have minus this term here times capital X1 minus k sub 2 these two should be equal to 0, no? Okay? Or you can do the same thing with this one, minus K2x1, and plus this one should be equal to 0, okay? So that means that above equation must be satisfied at any t, so at any time t, meaning that the term in brackets needs to be equal to 0. Meaning what? That minus m1 lambda 1 square plus k1 plus k2 capital X1 minus k2 capital X2 must be equal to 0. So it will be for the top equation, or the bottom one will give you what? Minus K2 capital X1 plus minus M2 capital lambda 1 square plus K2, K3 X2 equal to 0. Okay, so if you solve either one of these equations, or if you solve both of them, so solving about two equations, but not together, okay? I'm going to add here individually. Again, this is a lot easier than it looks like when you have numbers. So you will have x2 over x1. So let's do it together. The first one, if we use the first equation, what will you have? X2 divided by, so you move this one to the other side, will be equal to what? This term over here divided by K2, no? So it should be minus M1 lambda 1 square plus K1 plus K2 divided by K2 Now, if you solve x2 over x1 using the second equation, what are you going to get? You move this one to the right, so you're going to get minus K2. Wait, we'll move this one to the right. So let's see, you will have oh no, because here is point. Okay, no, yeah. So you will have K2, no minus K2, you will have K2 divided by minus M2 lambda 1 squared plus K2 plus K3. Okay, and here I'm going to add one little thing of notation. I'm going to add a 1 here, just meaning that this value of x2 of x1 is found for case 1. Okay? So now, what will be case 2? Case 2 will be when lambda square will be equal to lambda sub 2 square. Okay, I'm just going to say following the same procedure, you're gonna get capital X2 divided by capital X1. But this time I'm gonna add the 2 over here to show that it's related to this eigenvalue. And here you will have minus M1. So basically it's the same thing, but with lambda 2. Lambda 2 plus K1 plus K2. Basically it's the same. The only thing that changes lambda over K2 equal to K2 minus M2. This time will be lambda 2 squared plus K2 plus K3. All right, again, I'm doing everything symbolic. This is a lot easier once you start putting numbers, okay? But as I'm looking at this, you see, I just realized that maybe at the beginning of the program, I told you something not very correct, is that how many type of motions can we have? I told you 3, but it's not 3. What can we have? Either they move together, they can be moving together either to the right or to the left, okay? So that's one motion, and the other motion will be what? Each one moving away separately, no? But away from each other. So really, this how many type of motions we have? 2, no? Moving together or moving away from each other, not 3. And this will be given by what? So probably this one, the lambda one, will give you the response where both are moving together, I'm guessing, and this one will be when it's moving away from each other, no? Okay, all right. And this should be given by the ratio of this deformation. All right. Again, don't worry about notation. This becomes a lot easier once you start putting numbers. Okay, so over here, x dot, capital X2 divided by capital X1, this will be the eigenvectors, all right? So the eigenvectors, which is the way the mathematical name, but I want you to know them that they represent the normal, how do I call it, mode shapes? They also be called normal modes, but let me just call them mode shapes. Can be expressed as, and it's just the same thing. We have capital here, X1, X1 on top, not the bottom. So it should be 1, 1. So this is a vector. Let me put a line. X2 of 1. You probably don't understand why we're doing this now, but once we do the example, it will be very clear. So what you want to do now is to normalize. What means to normalize is to set a value as a reference. Okay? So let's see, if we use x1 here, we have x1, 1. And what we do is divide this one. So x2, 1 divided by capital X1, 1. And then this becomes capital X1, 1, 1. So here is nothing, okay? And if we do the same thing for the other one, we have X2 is identical. x1, 2, x2, 2 is equal to x2, 1, x2 over x1. I'm going to put the value at the end, would be easier, so it should be 2, 2, and 2. So these are the eigenvectors, but remember them as the mode shifts. If I have time to finish this. Okay, I will show you very quick at the end one problem. Quick, let's see if I can do it now. That way, maybe. Okay, so next class, probably we're going to be solving this problem over here. All right. So you see that we're going to get this one to be equal to 1, this one equal to 2.5. And now I'm just writing this under this form. So this, you don't know what is the deformation. You can assume one value. So you assume this is 1, what are you going to have? 1, 1, this is 2.5. So the first one is the same one for each one of them. So what is the first one going to tell you for this problem? If you have 1, 1, what does that mean? Is that at this frequency 1, when x1, when x2 is moving 1, x1 is moving 1, no? So this will represent that the both masses here are moving together, correct? Either to the right or to the left. Once we solve now for the second eigenvalue, the natural frequency, what's going to happen? This one is equal to ratio, let's assume it will be negative 0.5. Once we go and rewrite under this form, what are we going to get? If x1 moves 1, how much is x2 going to move? Negative half to the left. So this one will mean that when this one moves 1 to the right, this one will be moving half to the left. Okay? So this is what this is representing. Okay? All right. But again, that's not the total solution. This is just the behavior. All right. So the free vibration solution is obtained by replacing x1 and x2 into the assumed solution. So if you remember, what was the assumed solution? That was the assumed solution, no? Yeah? But we did everything. Okay. So we need one solution for x1 of t, one solution for x2 of t, no? All right? So in that case, we're going to have, let me switch colors, might be a little bit easier. We're going to have that x1 of t okay, so this one should be equal to what? Should be equal to x1 okay, let me just go directly to this one. It's going to become, so we're going to have x1, 1, e, I lambda 1t. All right, so we have this solution. This is x1, this is x1, no? Both are related to x1 here. This is for the first mode. So we have two of them. And the second will be x2 crazy notation, x2 1 over x1 times x, just rewriting this expression here, 1 1 ei lambda 1t and this, without going into too many details, will be equal to x1 of 1 sine of little omega 1t minus phi 1, and this one would be x2 1 divided by x1 1 x1 1 sine omega 1t minus phi 1. Yeah, I don't know. So x1, it doesn't matter, this is notation, and x2 basically will be exactly the same thing, but this time for the second one will be x1 of 2 e of I lambda 2t times x, I lose this expression, 2 x1 2 e I, oops, I forgot here to put an x. It should be x2 of 1 times e I lambda 2 of t, and this should just be equal to x1 2 sine omega 2t minus 2, and it should be x2 2 x2 1 times x2 1 sine of omega 2t minus 2. All right, so I'll stop over here. We didn't finish, but next time we finish this very quick. We're doing a numerical example. This looks complicated, but once you start putting values, it's a lot easier, okay? But this is just show the procedure really what needs to be done. All right, guys, there's one thing that